Welcome to this lecture on quantum, where today we explore one of the most profound quantum phenomena in modern physics, the fractional quantum Hall effect. This lecture is organized into 4 interconnected segments, each building on the last, tracing a journey from experimental discovery to the frontiers of topological matter and quantum statistics. These segments are 1. Integer versus fractional quantum Hall effect. 2. The Laughlin wavefunction and the quantum droplet. 3. Quasi-Holes and fractional charge in the quantum Hall effect. 4. Anyons and the birth of fractional statistics. Segment 1. Integer versus fractional quantum Hall effect. We begin by contrasting the integer quantum Hall effect, IQHE, a single particle phenomenon explained by the quantization of Landau levels, with the fractional quantum Hall effect, FQHE, a many-body phase that arises from electron-electron interactions. This sets the stage by highlighting how quantum correlations reshape the nature of quantization itself. Segment 2, the Laughlin wavefunction and the quantum droplet. Next, we introduce the Laughlin wavefunction, a theoretical masterpiece that captures the essence of the FQHE ground state. We explore how this wavefunction encodes correlation, forms a quantum droplet, and exhibits incompressibility. Through the plasma analogy, we interpret this state as a balance between repulsive interactions and background confinement. Segment 3. Quasi-Holes and fractional charge in the quantum Hall effect. In this segment, we explore the exotic excitations above the Laughlin state, quasi-holes and quasi-particles, which carry fractional electric charge. We show how these arise from local deformations in the wavefunction and how the plasma analogy explains their behavior as charge deficits, giving rise to one of the most striking features of the FQHE, charge fractionalization. Segment 4. Anyons and the birth of fractional statistics. Finally, we uncover the topological structure underlying these excitations. In 2 dimensions, particle exchanges are governed not by permutations but by braids, leading to a new class of quantum particles called anyons. These objects obey fractional statistics, and their existence represents a radical departure from the boson-fermion dichotomy, opening doors to topological quantum computation and beyond. Integer versus fractional quantum Hall effect. The fractional quantum Hall effect, or FQHE, is one of the most remarkable discoveries in condensed matter physics. Unlike the integer quantum Hall effect, where Hall conductance appears in whole number steps, the FQHE reveals plateaus at fractions, like 1/3 or 2/3, of the standard quantum of conductance. This difference reflects a deeper divide. In the integer quantum Hall effect, or IQHE, electrons occupy discrete energy levels called Landau levels, created by a strong magnetic field. When an integer number of these levels is filled, the system develops an energy gap, the cyclotron gap, which is entirely a single particle effect. It arises even if the electrons do not interact. That's why the IQHE is robust and was discovered first. In the fractional case, things are more subtle. The system lies within a single partially filled Landau level, and there is no natural gap between states unless interactions between electrons are taken into account. Here, Coulomb repulsion plays a crucial role. It reshapes the many-body ground state into a highly correlated quantum fluid. The result is a new type of energy gap, an interaction-induced gap, that stabilizes the fractional quantum Hall states. This gap has no counterpart in non-interacting systems. So the key difference is this. In the IQHE, the gap comes from the structure of Landau levels. In the FQHE, the gap is a product of collective interactions within the same level. But there's another mystery. Why are the conductance plateaus so flat and stable, even when magnetic field or density changes? The answer is disorder, which, ironically, helps. Disorder causes some states to become localized. These localized states do not carry current, but they allow the Fermi level to shift slightly without affecting conductance. Only when the Fermi level enters an extended state, capable of carrying current, does the Hall conductance jump to a new plateau. This same mechanism works in both the integer and fractional regimes. In the FQHE, The interaction-induced gap is carved up by disorder into regions of localized and extended states, anchoring the quantized values. But for this to work, the hierarchy of energy scales must be just right. The Landau level spacing must be largest, the interaction energy next, and disorder must be weakest, strong enough to localize, but not destroy the fragile correlated state. In summary, the fractional quantum Hall effect is not just a smaller version of the integer effect. It reveals a new quantum phase of matter, governed by interactions, topology, and emergent order, all within the same flat, two-dimensional electron gas. The Laughlin wave function and the quantum droplet. One of the most elegant ideas in condensed matter physics is the Laughlin wave function, proposed to explain the fractional quantum Hall effect at filling fractions like nu equals 1 over m, where m is an odd integer. To see what this means, imagine electrons confined to a flat, two-dimensional plane in a strong magnetic field. Their motion is quantized into energy levels called Landau levels. In the symmetric gauge, these single-particle states look like spirals, each with definite angular momentum. Now focus on the lowest Landau level and add interactions between electrons. This is where things get interesting. The Laughlin wave function was crafted to minimize repulsion while keeping electrons in the lowest Landau level. It vanishes rapidly when electrons approach one another, creating exclusion zones that keep them apart. As a result, the electrons form a uniform droplet of charge, a circular, incompressible quantum fluid. Its area grows with particle number, and its density encodes the filling fraction, nu equals 1 over m. What makes this state special is that it's not just a liquid, it's a topological phase of matter. Its defining features don't depend on geometry or microscopic details, but on the global structure of quantum entanglement. This makes the state robust against imperfections. But the system can also transition. At very low filling, below 1 over 70, the fluid becomes unstable. Electrons form a Wigner crystal, arranging into a triangular lattice. The Laughlin liquid and Wigner crystal represent two extremes, a quantum topological fluid and a classical electron solid. To appreciate the Laughlin wave function, compare it to the simpler case of a fully filled Landau level. There, the wave function is a Slater determinant, ensuring antisymmetry. In the lowest Landau level, it simplifies into a Vandermonde determinant, a product over electron pairs. Laughlin took this and raised it to the mth power to describe stronger correlations at fractional fillings. Now comes the plasma analogy, a brilliant conceptual bridge. The probability distribution of the Laughlin wave function maps to a two-dimensional classical plasma. In this picture, electrons act like particles with charge minus m, repelling each other logarithmically, all immersed in a uniform positive background. This background isn't arbitrary. It represents the external magnetic field and provides a confining force. Repulsion pushes electrons apart, the background pulls them in. The balance creates a stable, neutral droplet. This condition of neutrality explains the filling fraction. The negative charge of electrons is exactly balanced by the positive background, leading directly to nu equals 1 over m. It's not emergent, it's embedded in the very structure of the wave function. In summary, the Laughlin wave function describes a new quantum phase, an incompressible topological fluid. It explains the fractional quantum Hall effect as a collective phenomenon, not single-particle physics. Its mathematical form ensures correlation, its physical behavior mimics a classical plasma, and its robustness comes from topological order. Most importantly, the filling fraction, nu equals 1 over m, arises from the charge balance between repulsion and confinement, woven together by the magnetic field. The quasi-holes and fractional charge. Let's now explore one of the most fascinating features of the fractional quantum Hall effect, the emergence of quasi-holes and their fractional electric charge. In the Laughlin state, the most important charged excitations are the quasi-holes and similarly the quasi-particles. A quasi-hole localized at a point, denoted by eta, modifies the wave function by introducing a factor that vanishes at that point. As a result, the electron density drops to 0 at eta. Electrons are repelled from that region. The quasi-hole is therefore localized where the wave function is suppressed. It behaves as a topological defect and carries a fractional electric charge equal to plus E over m. To see this more clearly, consider placing m quasi-holes at the same location eta. The resulting wave function is mathematically identical to the Laughlin wave function with an extra electron at that point. But here's the key. Eta is not a dynamical variable. It is fixed and not integrated over. This means we are not adding an electron to the system. Instead, we are modifying the structure of the wave function to exclude electrons from that point. So what appears like an added electron is actually the absence of one. A cluster of m quasi-holes behaves like a removed electron, implying that each individual quasi-hole carries charge plus E over m. In this picture, an electron itself can be thought of as a bound state of m quasi-holes. But the quasi-hole is not a real particle that pulls electrons in by attraction. Rather, it is a puncture in the quantum fluid, a region from which electrons are excluded by the wave function itself. Electrons are pushed away not by a force, but by the structure of the many-body quantum state. This idea becomes even more intuitive when viewed through the plasma analogy. In this analogy, the squared magnitude of the Laughlin wave function behaves like the Boltzmann factor of a classical two-dimensional plasma. The electrons act as plasma particles with charge minus m, and the quasi-hole acts as an impurity with charge minus 1. This impurity repels nearby plasma particles, creating a local depletion of charge around eta. This exclusion zone behaves like a positive screening cloud. Its role is to cancel the long-range electric field of the impurity, producing a net neutral configuration at large distances. From this, we find the physical charge of the quasi-hole. The impurity has charge minus 1, and the electrons have charge minus m, so the ratio gives the quasi-hole charge as minus E over m. But again, the impurity is not the quasi-hole. It only creates the condition for the quasi-hole to emerge. The quasi-hole is the positive region left behind, the screening zone formed by the repelled electrons. It carries charge plus E over m. Thus, the quasi-hole represents a missing piece of the electron fluid, a topological excitation created not by classical dynamics but by modifying the global quantum state. Beyond quasi-holes, the system also admits quasi-particles, which similarly carry fractional charge E over m, but with opposite sign. In addition, the fluid supports neutral excitations, called magnetorotons, analogs of rotons in superfluid helium. These modes describe internal vibrations of the quantum Hall droplet and contribute to its excitation spectrum. Together, these exotic excitations, quasi-holes, quasi-particles, and magnetorotons, reflect the deep and subtle structure of the Laughlin phase, where topology and quantum statistics redefine what it means to be a particle. Anyons and the birth of fractional statistics. In most of physics, particles fall into just two categories, bosons and fermions. This distinction is rooted in the topology of three-dimensional space, where exchanging two identical particles either leaves the wave function unchanged or flips its sign. These are the only options because exchanging particles twice is topologically trivial. It's equivalent to doing nothing. But in two dimensions, something entirely new appears. Anyons, particles that obey fractional statistics. Here, the rules are different. Exchanging two particles twice is not the same as doing nothing. The paths they take can wind around each other, and this winding matters. Instead of forming a permutation group, particle exchanges in two dimensions form a braid group. This group allows for richer possibilities. When two particles are exchanged, the wave function can pick up any phase, not just plus or minus 1. If that phase is e to the I pi times alpha, then alpha can be any real number between 0 and 1. That's where the term anyon comes from. They can be anything between bosons and fermions. And it gets even stranger. In two dimensions, a clockwise and counterclockwise exchange are not the same. The system remembers the direction. This memory defines the topological nature of the excitation. In the fractional quantum Hall effect, the quasi-holes and quasi-particles are real-life anyons. They carry fractional electric charge, like minus E over m, and obey fractional statistics. The angle of exchange theta is 2 pi times alpha, where alpha is not 0 or 1. In some cases, even the wave function doesn't just pick up a phase, it rotates in a multidimensional space. These are the non-abelian anyons, the most exotic of all. So in 2 dimensions, particle identity is braided into the fabric of spacetime. And in the quantum Hall effect, anyons are not just theory, they're a measurable physical reality. One day, we may even braid them to compute. Conclusion. And that brings us to the end of our exploration of the fractional quantum Hall effect, a quantum phenomenon that reshaped our understanding of matter, interaction, and the very notion of a particle. We began with the contrast between integer and fractional quantization, traveled through the structure of the Laughlin wavefunction, uncovered the emergence of fractional charge, and ended in the exotic realm of anyons and topological statistics. What we've seen is not just a strange effect in condensed matter physics, but the blueprint for a new kind of order, where geometry, entanglement, and topology define the very fabric of physical reality. If you've enjoyed this journey through quantum complexity, be sure to subscribe, share, and let us know which direction you'd like us to explore next, be it black holes, consciousness, or the deep structure of space and time. This is Quantum, where physics becomes philosophy and philosophy becomes physics. Until next time, stay curious.